Dude Bam Bro, how are you? Today we're going to be talking about some basic trigonometry and calculus. Specifically, we want to answer what is sine x, sine x? What is sine of x? And we also want to know what a derivative is. This is to give you some intuition. That way, when I jump into the next couple of videos, which will be much harder math, I'm going to assume you already know some of this stuff. But I want to give those of you who have taken no math, because I was in that boat for a long time and I really wanted to know what was happening. I want to give you a conceptual understanding. That way, when you see things later, you'll know what's happening. That's the goal anyway. Some of you also who already know all this stuff may just find this a good refresher. It's going to be very intuitive. I'm not going to worry very much about numbers. I'm going to worry mostly about the idea of shapes and images for understanding. And so some of you may have not had that understanding before, so that'll be good. And we'll also be drawing a couple cool conclusions about phase and frequency that will be verified using the proper math in the next video. So, or in a video to come. So we're going to be talking about, what is this sine x thing? What is sine? What is that? If you've never taken trig, you're like, what the heck is this sine thing? You've probably seen a couple different things: sine, cosine, tangent, and then their inverses. Also, what's in here? What is this? Because this is an x, but some of you are probably more comfortable seeing a theta. You're pretty used to seeing that. So what is that? You know, that kind of a thing. So it all comes back to this circle. It all goes back to the circle, man. So the circle is the set of all points the same distance away from some middle point. And we see here it is. And if I scroll around the circle, we get a radius, and it's just tracing out the circles, verifying to us visually that they are all indeed the same distance away. Now, I could have pulled a trick on you with squeezing or stretching the axes and writing like an ellipse and squishing it and then making it claiming it was a circle. Don't worry, I'm not doing that to you. We have the hard math right here. So we see it's all the points x squared plus y squared, a distance 1 away. Now, don't worry too much about it, but just trust me when I'm saying this. So what we have here is we notice that when we do this, we can form a triangle from our point. So at our point, we're dropping this yellow line. This yellow line grows and shrinks, right? So let's just look at this as a point x comma y. So right, if this was a point x comma y, what is it? Well, this is the point 1 comma 0, because it's a unit circle, meaning they're all a distance 1 away. So of course, this is the furthest away on the x-axis. So if we're only on this line, what are the 2 points furthest from 0? Well, they're 1 comma 0, because this is as far away as we can get. Because as soon as we move up, our x value just got a tad bit closer to 0. We're shrinking on the x value now, but our y value is growing. So that's an important takeaway. And as we go to the other side, and we see, over here, we're at a value of -1. We're actually not quite at -1 apparently. So there should be some decimals there. As we see, we have a yellow line there. But basically, we're at a minimum. We're as far away as we can go from 0 on the negative side. And that's as far away as we can get. So the furthest we can get away is either -1 or +1. And this actually holds true for y as well. If we look at y, we notice now, just ignore this bit here. This is radians, so I'm going to write in something a little fancy. So here we have radians, and we notice that when our y is at its maximum value, our x is at 0, and our y is at 1, meaning our xy coordinate, there's 1, and if of course we go down, we'll get a 0 and a -1, which would be 3 pi over 2. And now we say, look at that, we are at our negative value. So we can see visually confirmed that this is how this works. Now we want to know, now let's talk about what is this thing called sine. What is sine? What the heck are you saying when you say sine of something? Well, some smart dudes, maybe some smart women, this is a history thing. So unfortunately, there's a whole oppression business going on then. Today, we would say smart people. So some smart people came up with this notion that they were like, look at this. When I move this radius around the circle, this is x value doing some, and y value doing some suspicious business. It seems that the x value and y value shrink to always make this 1. They're always making it true that this line has to be 1. The radius, or if we look at this as a triangle, the hypotenuse is always the same distance. And they're going, listen, they're collaborating together to make this happen. And so because of that, we said, well, let's look at this from the view of the angle. So here's an angle, and we say, well, look at this. It seems that if we take the opposite of this angle, which is this side here, so we call that y, since it's how high we are, so it's the y value, over the hypotenuse. That's what sine is defined as. So sine of some theta, which is just some angle. We just use theta. It's like our thing to use. That's just really the height of that yellow line, the opposite of this. So there's a variety of ways people learn this. So we have opposite over hypotenuse, but it's also the opposite's really just this yellow line. That's really just y. And our hypotenuse is really just the radius r. And in this case, it's really just 1 because that's how big it is, and it's always 1. And so we end up getting that sine theta is equal to y. Now this is a unit circle deal. This doesn't always hold true. Sometimes our radius is not 1 and we have to do other things. But that's what sine is. It's basically saying, hey, on the bottom, put this length, and on the top, put this yellow length. And we notice that the yellow length, the biggest it can possibly be, is the same length as the blue length. So if I move over to pi over 2, they are the same length here. And so if you put that length over the length of the same size, then you get 1. So we say that when we put the angle, when x is 0, we get a y of 1 for sine. So if we had sine x, and we had, in this case, if I put, okay, so let's really quick talk about this, because this is gonna be, you might meet some resistance here. So let's say I put sine x, and then I'm saying, when x is 0, we should get a sine of 1. But the thing is, this x value in here isn't really like x values. This x value is an angle. That's why we often put theta. So if we put theta, but we don't have a theta axis, we have an x axis. So what it does is it takes x to be an angle. So you put an angle in. So here's an angle. See, we're picking angles, and you're going to get out specific functions. You're going to get out some y's. So what angle was needed to make x 0? Well, if we look at this, x is 0 on this circle when we move to 90 degrees, because we had a right angle. So at 90 degrees, x was 0. Now I'm using radians to make the graphs a little more reasonable size-wise. But if I put in the equivalent of 90 degrees in radians, which we're not going to talk about what that is, but just know that this is 90 degrees, which is pi over 2, we will get 1. As we can see down here, we get 1. So that makes perfect sense. And if we look at our graph of the function itself, we see that at pi over 2, we are at 1. And then at pi, which if we move 1 length pi, which actually puts us right here, our sine will be at 0, right? Because we've not gone up or down at all. So it's really just the ratio of this triangle. Now, the opposite, hopefully I've still got you. So for some of you who've never seen that might be a little bit of you need a break here to really think about, is this true? And work it out in your own head. But we have the same things true for cosine. So in cosine, this time, let's look at that. Remember, this x is an angle. It's not like the regular old x values. We're putting in angles. So, and that can be a bit confusing. So now we can look at cosine. So if that's sine is just the opposite over the hypotenuse. And so when we're at 0, right, sine is at 0 because it's as small as it can be. It can't be any smaller. It's 0. And then on the other side, when we're at -1, again, sine's at 0, or as small as we can be. So this explains the up and down motion of sinus is growing and shrinking. If I hit play on the slider, We see this growing and shrinking. Now we notice X also does this growing and shrinking business. Look at the X is getting shorter, now it's at 0, growing, and then it shrinks. So we say, we could define this, instead of using the opposite side, we will use this side here, and this side, it's not opposite, it's adjacent, right? It's next to this angle, so we're just gonna call that the cosine. And so it's cosine because it references the x-axis. And so we say, okay, interesting. So when we do that, if we start at 0, we notice cosine has the same length as this line. And so our cosine will be 1. And sure enough, if you put in cosine of 0 degrees, remember, it's a cosine of x. But if we put in cosine of 0, we get out a value of 1. And that's because if you've moved 0, and remember this is degrees, remember this x value represents an angle, then that's what's going on. And the reason it's an angle is because we always look at this stuff with respect to the angle. So if we pick an angle of this, so as we move around here, now I've again chosen radians, not to confuse you, but that's just how you work with circles. You get so used to radians, you don't even think about it. But just so you know, yeah, so we have 90 degrees, we have 0 degrees or 180 degrees, so we've moved around half a circle, then we will again reach a negative, the maximum negative value, or the minimum value, I should say, of, 3.15. It's pretty dang close to pi. We will reach it, so that'll be when the cosine is -1. For that reason, when we're over here, that's why cosine starts up here. Now, I want to bring in some cool facts about phase. So if I move around, I've now made it so that you can see the graph of sine. And you see sine immediately begins to grow, and it always maintains the same y value, because remember, it's this y value over the hypotenuse, which is 1, which just gives us y. So this y value will always be the same value here. And as I scroll along, we notice they maintain the same height, again, because of the whole y business. And we look at this, and for those of us in audio, we are usually taught that about phase offset. We care a lot about this phase offset because that could really, if we have two waves that are the same and one scrolls over a bit, they'll like cancel and it won't be that great. So we want our phase to be the same. But what people don't tell you, and in math they beat it into you, is that every single point on this sine wave, actually in math they don't really beat it into you. You have to take like a physics class for it to really sink in. Every single point on this wave is also a phase, right? Because it's coming from some specific angle on here. And so when we say sine of x, we call the x the phase. And it's a measure, it's an angular measurement. And so that's what our x is. So let me get rid of this. So we notice that this specific instance of phase gives us this specific point on the sine wave. They are related by an angle of measure. All the sine wave is an expression of this. If I move it back, we see it undo itself. So we say that, oh, phase is angular measure of a sine wave. And it's actually also true for cosine, right? If I use a cosine wave instead, we start at 0, which is a specific angle, angle of 0 degrees. As we move around, we get this. We are talking about instantaneous phase because we're looking at phase at this specific instance. So as phase moves along, we notice our wave develops. And now let's talk about frequency. Now we don't have a frequency defined here. Like if I have sine of x, we don't know what our frequency is here because we're not told explicitly what it is. It's in there. Now we call the entire function here the phase, but it's confusing because, you know, where's the frequency? How do we know how fast this thing is? Because if our triangle spins around fast, we'll get a high frequency, right? Because it will draw waves quickly at some rate. And because of that rate, we'll say, oh, it's this frequency. So we can actually specify this. If I say like, so this X thing isn't quite cutting it for us. So I might say, I want a frequency of 3x. And then we say, oh, look, it's going faster because now whatever our angle is, it's gonna pick that at 3 times as fast. So we could say arbitrarily that fx will give us our frequency, but we should also, it's good math manners to also state your period, which in this case is 2 pi. So that's basically just how big around the circle is. And when we do this, I'm getting into the math now, so I'm gonna stop at explaining this. But when we do this, we are now explicitly able to state a frequency. And you saw that had an immediate effect on our wave. So it's like, oh, okay, here's 3. And we're able to see that this is a faster frequency, 5 is a faster frequency, 6 is, and so on and so forth. 100, it's like crazy. And also, fun fact here, if you notice, if you're really paying attention here, we notice that our slope gets steeper and steeper the higher the frequency goes. So right, this is like not very much, the rate of change is not very quick, and it's sort of like a drawn out line. But if I have a frequency of like 500, and then we zoom in here, we notice that these look very much so like straight lines. And that's actually a really important property, that as frequency goes to infinity, we essentially get just, well, not essentially, you get a straight line because it's infinite frequency. Like it goes up infinitely. Like, where does it turn? No one knows. It's infinite. So that actually has a special name. It's called an impulse response. I can never say the D version of it properly. It's like the Dirac impulse. I've heard it said, I've read it in my books. I might be Dirac, whatever. You can look it up. It's a cool thing. So, okay, so that's sine x, that's cosine x. Hopefully you get the idea. There are these triangles spinning around inside of circles. And that was just a random cool fact that actually is really useful for a lot of digital signal processing things. But now let's talk about the progression of phase and frequency. So we just saw that frequency, is if we have our x multiplied by some value, it's gonna happen a lot faster. So what we end up saying is that that's right, how fast it spins around defines a frequency. So we can say this, the progression of phase is frequency. That actually is a derivative, and we'll actually prove it in the next couple videos. So if my phase progresses quickly, the angles move around quickly, then I will have a high frequency. If my phase progresses slowly, then I will have a slow frequency. For this reason, if I change the phase of something, I'm messing with the frequency. And if I change the frequency of something, I'm messing with the phase. And this brings us to the derivative. So I'm gonna kind of stop here. If you have any questions, feel free to let me know. I'll put this link in the description. We're gonna jump over to what it means to have a derivative. So here is a function of sine x, but first, let's just do something, the classic derivative, x squared. This is it, man. They're in a Calc 1 course and they tell you this. Now, I'm not gonna get into secant lines and approximations and Riemann sums and everything. That's like for the math class. We just wanna understand some stuff for digital audio. So we say, okay, this is a line. Oh, let's do that. Let's start with that. That's the best way to do it. This is a line. And we say it's the line y equals x. And if we take, the question is, what is the slope of this line? So if you remember from your math class, we have y equals mx plus b. And the slope is m. But I promise to be visual, so it's just how steep this line is. So if we say, is this point on the line, let's say we look at this section, is this section of the line any steeper than this section of the line? We say, no, it's the same steepness, no steepness change. So we say the derivative is the same. Basically, if you have a change in steepness, you have a change in the derivative. So here, since there's no change, the derivative is a constant value. It's just a number. Nothing changes here. And so our derivative stays the same. So if I took a derivative of this, I would simply get out a number. That's the takeaway from this. It's all you gotta know. If I take a derivative of a straight line like this, I get a number. Now, if it's a vertical line, it's undefined. If I have like x equals 4, so here's x equals 4, and if it's defined as a slope, right, we have rise over run, but this thing, it rises infinitely and runs nowhere. So that's infinity over 0. Like, what the heck is that? We could get all philosophical. But for that reason, we don't like to talk about these things. And in digital audio, if you try to take a derivative with something that's got a sharp corner or a line, you'll get a pop or a click. And now if it's a sharp corner, it'll actually just go from one constant, because that's just a line. So it'll be one constant to another constant, whatever the slope of the next line is, because we can do that. But at this specific corner, things get political, and things get political when we get straight lines. So square waves, that's why they click and pop the way they do. They're going instantaneously from like this to this. So if you were going from here and here, this gets into the limits though, and I'm not gonna talk about limits, but basically that's so straight up and down lines and sharp corners give us some problems. And in audio, we hear them as clicks and pops, and they can actually be used really musically. Now here we have the steepness of a line. So that's the derivative of this is just a constant. Now if I change the steepness of the line does not change anywhere here, right? It's the same all the way up and down the line. So again, we get a constant, but it's a different steepness. So the derivative would be just a higher number because it's more steep. If I go to 6, 7, 8, let's say I go to 233, we get a very steep line, but it's still just a line. Now let's make the jump. Here we have sine x. Let's give sine x some amplitude so it's not so small. Okay. If we scroll along this line, the derivative is no longer a constant. Now, we see that what we do is we take the tangent line. So if we put a point on this line, the tangent line at that point is the derivative. So the slope of this guy is the derivative of this function at this point. So basically it's how steep is this function at that point. And we say, well, it's this steep. If you had a line there, this is how steep it would be. If I scroll down, we could see, oh, this is practically flat. Like if you were hiking, let's say you were hiking along this thing and you're going up, oh, it's so hard. And then you reach the top and then you go, oh, wow, look at that. This is the easiest part of the hike because it's basically flat up here, right? So you stop at the peak and you're like, oh, this is great. Someone's gonna take this conversation and turn it into something weird. I just know it. So as we scroll down, we see the same is true at the minimums. So this is the meaning of derivative. How steep is it? Now it turns out that we see that over time, this derivative is changing. And actually, I don't wanna take the time now to explain the whole reason, but it actually ends up being that the derivative of sine is cosine. If you were to graph all these derivatives out, you would actually see that it's cosine. It's a 90 degrees phase shift of just sine. So that's like really crazy. One thing I didn't talk about with sine and cosine, I just remembered too, that I need to talk about, is that if I have a graph of sine of x, we were just looking at cosine. You might say, in audio, I only ever see sine. Why isn't cosine ever brought up? Well, it's because cosine is really just sine x with a phase shift. So if I just add a little phase shift here of pi over 2, which again is 90 degrees, I get cosine. So if I put like cosine down, you see if I take it on and off, it's the same thing. So all we do is we say, and I can actually make this some arbitrary value like p, and we'll make a slider for it. And I can actually shift the sine wave around by adding a phase offset. Now this is in audio, the thing that everyone seems to know about. So I can add a phase offset, and that's what's going down there. And so for this reason, we just talk about everything in terms of sine waves that have just gotten some phase offset instead of dealing with cosine waves. But cosine is really important for math and some identities and a bunch of other things. But for now, that's why you usually only see sine. And then we deal with arbitrary periodic functions, which I'm also not going to talk about here. But so we tend to do that instead of using cosine. But you can totally do it. If you open up Reactor, there's cosine stuff in there. Okay, so anyways, yeah, this is the derivative, how steep a line is, and the derivative of sine is cosine, because if you look at this, it actually correlates, because look at this, when our derivative is a flat line, this is basically 0. When we get to a horizontal line, right, that's a flat line. Well, what's its slope? Its slope is 0, right? Because if we have rise, are we rising over anything? No. And are we running? We are running. Now, we run into a similar conundrum here, where the rise, we don't rise any, but we run an infinite amount. Like, what does that mean? Because, right, we run forever in each direction. This is a little bit confusing, but it's easy to see that if we have a local area, like if we just pick run from 0 to 3, and then we do that, we pick 2 points and then we do it, we'll get 0 as the slope. For the case of the straight up and down line, because if we scroll down here, we notice there's no point where the line goes straight up and down. If we put y equals rise, or not y equals rise over run, if we have rise over run, and our rise is infinity, and that goes over no distance, like you can pick points on that line for the y, because if we had like x equals 3, you can pick points, but this will always be 0 underneath, so there's no way of even locally proving that this is going to work out. So for that reason, we say that this one's undefined. But anyways, if we pick this, we see up here our derivative is 0, and this will actually correlate because we know the peak of the sine wave correlates to a 90 degrees pi over 2. We just saw that in the circle when we're at the top of the circle. And so because of that, we say, oh, well, look at this. That means that this must be the cosine is at 0. When sine is at its maximum, the derivative is at 0, which correlates to cosine. And if we scroll across again and we get to the minimum, which we know is when the circle is right here, we expect our cosine to again be at 0, and it is. And it turns out every single other point in the middle works out. And so we can actually see visually that this is indeed the derivative of sine is cosine. So anyways, derivative is how steep something is. So if I were to pull open an FM synthesizer, so here's an FM synthesizer, and we were to look at, we want to FM something, we can visually see, well, this is a derivative, and we just saw that this line is constantly changing because the slope, how steep it is at every point, is constantly changing. And as a result, we get that constant movement that we know and love. But if I move it to become more like a line, we see that now the derivative will just be some number, and then it changes here to some other number, and then it changes back to the same number as this one because they have the same slope. And so that's why we get the two tones above and below. That's what's going on. And then as we change here, it's still just going to be two tones, two tones, two tones. And as soon as we get to a line, a weird thing happens because it tries to go from this all the way up to this. And so we get some clicks and pops and things. And as we scroll along, we now introduce another line that introduces more pops. So things get weird at these points, but they become pretty useful. And so we're going to be talking about what's going on here. But anyways, that's why like the sine wave will be woo, 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 why the triangle wave will be like doo, 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 doo. That is the secret behind those things. If you have any questions about this stuff, let me know. Hope I was pretty straightforward. We're going to be diving into sort of watching the actual math and seeing it unfold before our eyes. But this is a very visual way of getting a grip on these two concepts. So just as a quick review, derivative, how steep you are. If you're a line, your steepness is staying the same, so nothing changes. If you are a curvy thing, your steepness is changing. And so we call that the derivative. We use secant lines and things to get that, which we did not talk about in this video. But if you want more information, you can go look it up. Just get a basic calculus book. Next, we have sine, the progression of, or trigonometry that I should say. And when we have something like sine x, we are simply picking an angle and comparing a ratio of these sides of a triangle inside a circle. And the big takeaway from this is that sine x, the progression of phase is frequency. And so they are linked to each other. And also in the function sine x, the inside piece here is called the phase. That's important. Now, we did not expand x in this video. We are going to in the bigger video. But when you see me doing things with the derivative, we're talking about the rate of change that's going on, talking about the steepness at the different points on the function. And so you could just sort of think of that while we're talking about those things. And the inside is called the phase. We get a lot more specific and we actually define a frequency in there so that we can specifically talk about frequency and phase on an independent level. If you have any questions, again, let me know, subscribe, and have a blessed day.